that regardless of the angle, it doesn't matter whether it's pi over 3, 135, 11 pi over 6, 23 pi over 7, 0 degrees, it does not matter the angle. When you take the value of sine of that angle and square it and add it to the value of cosine of that angle squared, it is always, always, always going to equal 1. I could go through the proof. I'm not going to go through the proof at this time. I probably will later on this semester. But all you need to know right now is that that is equal to 1. So we call this the Pythagorean identity. And the reason why it's named that has to do with how it's actually proven. But all you really need to know is that sine squared plus cosine squared is equal to 1. So some derivations of this identity we may need to use. So we've got sine squared plus cosine squared is equal to 1. If we take that entire equation and divide it by sine squared, which we are allowed to do, because as long as we do it to the left side of the equation and to the right side of the equation, you haven't actually changed anything. Okay, when we simplify this, sine squared divided by sine squared is 1. Cosine squared over sine squared, well, ignore the squared for just a second. Cosine over sine is equivalent to cotangent, and as long as they're both squared, then we can say, well, that's also equivalent to cotangent squared. Same thing with 1 over sine squared. 1 over sine is cosecant. So since it's squared, we can just say that that's equal to cosecant squared. So that is a derivation. If we go back to the original, and instead of dividing by sine squared, we divide by cosine squared, we will get this result. Sine over cosine is tangent. So that's tangent squared of x. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So there are 3 versions right now of the Pythagorean identity. They are all derivations of the Pythagorean identity. Technically, there are 6 more. Now, I'm not going to get into all 6 of them. I am going to give you a little sneak peek here with the last one. We can rearrange that equation. We're not going to change it. We're just going to rearrange it. Depending on what information we have, we may need secant squared and tangent squared on the same side. So if we move the tangent squared over, we're going to subtract tangent from both sides. Well, tangent squared, actually. So we could have that equation. 1 is equal to secant squared of x minus tangent squared of x. That's another version of it. Or maybe we wanted tangent squared by itself. So we subtract the 1 from both sides. So tangent squared is equal to secant squared of x minus 1. Today, we're just going to focus on sine squared plus cosine squared, but we may need those others somewhere down the road. Hello. Okay, train of thought. We could do the same thing to our 1 plus cotangent squared is equal to cosecant squared. We could do the same thing there. We could do the same thing to the sine squared plus cosine squared is equal to 1. but we're going to focus on using the sine squared plus cosine squared is equal to 1 today. All right, so let's look at another example here with eliminating parameters. Okay, eliminating parameters. We're going to eliminate the parameter and identify the curve. So we've got x is equal to 2 cosine of t, y is equal to 2 sine of t, and we are told that t is between 0 and 2 pi. All right, so if we handle this like we were handling our previous problems, we want to solve one of those equations for t. I don't know about you, but I really don't want to solve either of these equations for t because that's going to involve inverse trig. That's going to require either the inverse cosine or the inverse sine to get the t by itself. So I don't want to go there. But what we are going to use is what I just showed you, that sine squared plus cosine squared is equal to 1. So what we are going to do is in both of these equations, we are going to isolate the trig function. So in our x equation, we're going to divide both sides by 2. In our y equation, we're going to divide both sides by 2. Okay, again, we're not going to isolate t in either one of these because it would involve inverse trig and then plugging an inverse trig into another trig function. That's really complicated. So what we are going to do is we are going to square both sides of both of these equations. Which again, we are allowed to do. If we do it to the left side, as long as we do it to the right side, we are within the rules of arithmetic. Okay, so if we square x over 2, we get x squared over 4 is equal to cosine squared of t. If we square y over 2, we get y squared over 4, and that's equal to sine squared of t. Now, I told you we were going to use what we just covered, that sine squared of x plus cosine squared of x is equal to 1. Well, don't I have something that's equal to sine squared of x, or in this case, sine squared of t? I do. Y squared over 4 is equal to sine squared x. So I'm going to replace sine squared of, you can change the variables. Okay, nothing crazy going on there. We're just going to replace it there. Cosine squared is equal to x squared over 4. So we're doing a substitution, but it's not exactly like we did the substitution when we first started eliminating parameters. And that's equal to 1. Now, traditionally, you will see this equation without those denominators. If both of them have a denominator of 4, so if we multiply the entire equation by 4, we get that y squared plus x squared is equal to 4. Now, does that equation look familiar to anybody? Common shape. Math 2 or Math 3. Circle. X squared plus y squared is equal to r squared. This is a circle with radius 2. Okay, that's a circle with radius 2. Now, with the help of Desmos, we can graph this very easily. We can just type in y squared plus x squared is equal to 4. It'll graph the circle, no big problem. Well, before the invention of Desmos, you could not easily graph this. You could isolate y. You could move the x squared over, you could take the square root, and you'd have to put it in your calculator as the positive square root and the negative square root. Well, with the help of parametric form, we can graph this circle a whole lot easier. If your calculator's in parametric form, put in 2 cosine of t, 2 sine of t, and go to your window. Our t's between 0 and 2 pi. And let's change this back to, let's go negative 5 pi. That would be big enough. Okay, and you can see now, it doesn't look like a circle right here. It looks like an ellipse. The reason for that is because your calculator screen is wider than it is tall. So if you do zoom square, it will fix that X dimension so that it's proportional to the Y dimensions. So it looks a little bit more like a square. Our calculators are still limited in their resolution, so it looks, did I say square? Circle. I said square because it just looks like a rounded square, doesn't it? And I was talking about the square window. But yes, sorry, this is a circle, obviously. I'm not going crazy yet. That is a circle. All right, so let's look at another one. X is equal to 3 cosine of theta, y is equal to 2 sine of theta. Okay, so similar idea here. We're going to divide both sides by 3. So x over 3 is equal to the cosine of theta. Y over 2 is equal to the sine of theta. Okay, we are going to use sine squared plus cosine squared again, so we need to square both sides of both equations. So we get x squared over 9 is equal to cosine squared theta. Y squared over 4 is equal to sine squared of theta. Let me rewrite my Pythagorean identity again. So you can see the substitution. Y squared over 4 plus x squared over 9 is equal to 1. Now this one, they don't have the same denominator. So we're just going to leave it. Okay, we're going to leave it just like this because they don't have the same denominator. It's not a circle. Okay, it is not a circle. Let's look. My window's already squared up. I don't need to change anything else. Now, this one is supposed to look like an oval, or in our class, we're going to call this an ellipse. We will study more about circles and ellipses and a couple other functions like that coming up soon. But for right now, you just need to know that that is an ellipse. Okay, any questions?